Good morning, mathematicians. What do we got for you today? I've got a story for you later when more people show up to the stream. But we're back. We're back to a slightly earlier time, so that's good.
Good morning.
But what are we going to do in the meantime? What am I going to yap about? It's always the question. Good morning. I like the Aleph Null symbol there. Are you a fan of the channel Aleph Null? Hey, Edit Smith. Yeah. So what are we going to talk about today? Until other questions start pouring in. Maybe I'll just make you look at me scroll through the PDF I was just looking at before I started the stream. About some Langland's nonsense. I'm trying to find a very particular example. This is a paper that has a whole bunch of representations of p-adic sp4, symplectic group sp4, and I'm trying to figure out some things about it in the context of the Langland's program. In particular, there's these representations, which, as you can see, are some sort of induced representations that are very special in theory. I'm trying to see if that actually showed up somehow in some example I was looking at. Oh, also, what an amazing name. Fixator. Fixator. Wow. Love it. Absolutely love it. So yeah, this is what crazy Langland's looks like when you work out a whole bunch of stuff by hand. But I don't know where the thing is that I'm looking for. Oh, but I do have this for you. By popular request, and by popular I mean one person commented on a previous comment, we're going dark mode today, and maybe for the rest of time, if people prefer it, which I think they do. Yeah. Also, I don't know, like, is Galaxy Pen too annoying for most people? I feel like Galaxy Pen looks so awesome, especially on this black background. Why don't I just tell you guys about, I don't know, what should I tell you about? What should I yap about today? Maybe I'll tell you about symplectic groups. Oh. SP4. Yeah, no, that's too crazy. I don't know what I was thinking. I'll tell you about some of the algebraic groups that I work with. So, maybe I can even do some relevant computations here live on stream. Maybe that's worthwhile. Yeah. So, well, generally, these sort of groups that I think of, normally there's different ways you can write them, but one way to think about it is, so we've got the general linear group, right? If V is an n-dimensional vector space, say over the complex numbers, this will just be isomorphic to the GLN over the complex numbers. That's just the group of all automorphisms of the vector space, right? But now we could also have a pairing So for example, the dot product on Rn, so it eats two vectors in Rn and it spits out a scalar. It's bilinear and symmetric. So what does that mean? I mean, so bilinear, that's like alpha, a scalar dot v is equal to alpha u dot v, for instance, or u plus v dot w is equal to u dot w plus v dot w. So we have some sort of inner product. And maybe we want to study the linear transformations that preserve this inner product. So what I mean by that is a linear transformation preserves the inner product if for all u and v, t of u, t of v, inner product is the inner product of u and v. Oh, I just realized, I saw you said yeah forever ago that you were a fan of the channel Aleph Null, and then I didn't realize what that yeah was in response to. Yeah, I love that channel. I think it's one of the best math channels on YouTube. And actually, I met him in person. We chatted a couple times just over Zoom, but then I met him in person at CMS. It's the Canadian Mathematical Society. It's like a meeting that happens twice a year where you go and give talks. And it's really expensive, so I kind of hate it for that. But I guess I need to go give talks so like people know I exist and know about my work. Lots of other conferences are free. This is my advice to everyone always is apply, even if you're an undergrad. Apply to as many conferences, workshops, summer schools, blah, 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 that you possibly can, because sometimes you'll just get to fly around the world and do math, and you'll just get to fly somewhere for free. Yeah. So keep that in mind. Anyways, cool dude. I wish we had gotten to chat longer, but there was a lot of talks to go to. But to be honest, on the last day, I kind of ditched some talks because I was like, nah, I want to go see the city that we're in. It was Vancouver. I've been there before, but yeah, I don't know. Sometimes you got to go walk around in the woods with your main homeboy talking about math. Anyways, so we've got so suppose we've got linear transformations preserving this. Well, linear transformation. So remember for GLV, the group of isomorphisms of a vector space, that was isomorphic to GLNC, right? So, and we know that we can represent linear transformations as matrices. So we might want to ask, how can we take this condition and encode it in terms of matrices? So, well, one thing we'll want to do is maybe take this condition and encode it in terms of some matrix, right? So the process by which we write these the linear transformations in terms of matrices involves us also representing our vectors in terms of matrices by choosing some basis. So in that case, if now I'm thinking of u and v as column vectors, normally an inner product, and so some sort of, doesn't always have to be symmetric, as we'll see in a moment, but some sort of like bilinear pairing that eats vectors on either side and spits this out. Well, how could we represent that? Well, with a matrix. So we can find a matrix such that the inner product of u and v, well, in this case, the matrix that we put in the middle is just the identity. that will return the dot product for us. So you take U transpose, multiply by I, multiply by V, you'll just recover the ordinary dot product. So what would it mean for a matrix to preserve that? Well, let's write out the equation, right? So it would be U T I V equals the inner product of U and V, which is T preserving by assumption. So then what is this? This is, well, T, so let's write it in terms of a matrix form. So maybe I'll write A for the matrix associated to T. So I can write this as A times U, inner product with A times V. But that's going to be, by our previous formula, that's AU transpose times the identity matrix times A V, which would be U transpose A transpose A V. And so if this is going to be true for all vectors V and U, that's only going to hold if you range over all possible U and V. That's going to hold if and only if A transpose T, A transpose A times A is the identity matrix. So this is what we would call the orthogonal group, or the yeah, right. So this is the orthogonal group, say, of the vector space and the pairing. And we can realize it in terms of matrices. So this is isomorphic to what we might call ON, I don't know, let's say over the reals, or it could be over anything, but this will be ONR, where what is this? It's the collection of all matrices. So there's still isomorphisms of the underlying vector space, so they're in GLNR, but they also satisfy that A transpose A is the identity matrix. So in general, one way, so a very important and interesting class of examples of, say, real Lie groups comes from basically choosing a vector space and some kind of inner product, and taking the group of what we might call isometries. So that just means the linear isomorphisms of V from V to V that preserve the inner product. So for GLN, there's no inner product. For ON, right, this basically preserves the dot product. So if you take, so let's look at a complex vector space, and let's look at the Hermitian inner product. So basically this is the one where you sum over U and V conjugate, the entries of the vector. So almost like the dot product, except you conjugate this other one. So that the group you get out of that is the unitary group. What are some other examples? So another example we could choose for another important example in like physics and stuff is the symplectic group. So here, the matrix that we choose, so I mean, I can tell it to you defined either in terms of the pairing, right, by this equivalence above. So all our pairings are just going to be given by some, can be defined in terms of just picking some matrix that's going to go in the middle, right? And then the properties of the matrix should correspond to properties of the of this. So lo and behold, the matrix you put in the middle for a Hermitian thing should be a Hermitian matrix, for example. And so for the symplectic form, this only exists for even matrices of even square size. So sp2n is defined to be the matrices preserving the form. So let J, this will be the n by n anti-diagonal matrix. So formally, its entries are given by the Kronecker delta of n plus 1 minus I and j. And so we just have ones on the anti-diagonal. And then we can define a bigger matrix, omega, and we'll define that to be 0. So this is a block diagonal matrix now. So this is 2n by 2n. This would be 0j minus j0. So one way to write down the symplectic group, say over a field F, is to write it as all of those matrices in GL2NF such that, these matrices have to preserve the form just like before. So it would be, but in this case, it would be A transpose omega A equals omega. Wow, Chad is dead this morning. Either no one's got any questions, or maybe you're all just mesmerized by doing matrix groups in dark mode. I don't know. Maybe it's because I suddenly started early again. Anyways, so this is one way to define the symplectic groups, and there's Tony Lyon, master tweeter is in the chat. Math comedy goat, I would even say. I would even go so far as to say that. So we've got a bunch of different. There's one thing. There's oftentimes when people say the word classical group, they mean one of the following things. So they mean either so one thing I didn't say is, so here we defined ON to preserve the dot product, but there's a special subgroup of this called SON where we ask that the matrices also have determinant 1. Got here late, don't know what we're doing. What are we doing? Well, basically, I'm just yapping until people have their own questions that they want to ask me. So I decided to start yapping about matrices and matrix groups and talking about important examples of matrix groups that are defined as collections of linear transformations preserving a pairing and connecting that between sort of our matrix realizations of these things. So that's what I'm on. That's what I'm on now. Until people got their own questions. I've got a story for y'all later. Maybe when a few more people come into stream. I've got a story about how research is funny and how it works. So these classical groups, we've got SO, but I'm gonna break them into two separate categories. So I'm gonna call SO SO2n and SO2n plus 1. I'm gonna write those two things as slightly different. and then there's sp2n. So these are the so-called classical groups. And one reason why I'm writing out SO2, so SO even and SO odd a bit differently is because there are different things about them. So one fancy way to say is that they have different root systems. So there should be some way in which you should believe that these two somehow you should separate SO even and SO odd. There's something different about them, but I don't know if I'm going to get into root systems yet. One thing I will say, though, there's this notion of dual group, which I also won't get into quite yet because that has to do with root systems and stuff. Or maybe I'll start yapping about it. I don't know. But it turns out that SO2n is self-dual. Meanwhile, SO odd and sp2n are dual to each other. So there's a dual pair. So that's another sort of way in which they're different. So in some sense, actually, maybe surprisingly, you should think of SO odd and SP as somehow those are more spiritually related actually than SO even and SO odd. So that's kind of neat. You wonder if any linear group can be defined as matrices preserving some set of tensors. Probably because here's a great isomorphism. That's maybe something I should make a list of too. What are my favorite isomorphisms? What are my favorite isomorphisms? I don't even know. What's a good color? I feel like the only problem with dark mode is dark mode has a less interesting color palette. Not that I used all of the colors anyways, but I feel like there's more purples and blues in light mode. But, c'est la vie. Probably you could make it as preserving some set of tensors or something. And here's part of how I might think about doing that. And if I get sidetracked, too bad. This is a great isomorphism. So the endomorphisms of a vector space V are isomorphic to V tensor V star. Maybe I should write V star on the other side. I think I like to think about it that way. I mean, okay, the tensor product of vector spaces is symmetric, so up to isomorphism, it's not such a big deal, perhaps. But so we could write it as something like this. Well, okay, actually, before I even dive into that, let's just think about the fact that what is a bilinear map? I mean, a bilinear map is a map that's well defined on tensors, right? So, if you have V, the Cartesian product of V to R, you have some sort of pairing. It's a bilinear map. Then, by the universal property of tensor products, you get a unique linear map on the tensor product. So, in a sense, yeah, the answer is just yes, right? The answer is just yes. Well, I've written this in terms of a map, rather. So what this means then is that, like, if you have a linear transformation that preserves this bilinear map, then I guess the induced linear transformation on the tensor product should also preserve this map you get on the tensor product, right? Like yeah, because T of U tensored with T of V, that's going to be, so write this as the projection map. I mean, that's just the projection applied to, what am I going? Oh, I got to rewrite things slightly. That's not the eraser. Oh, and my eraser's forsaken me now. Okay, I'm on my own. So this should be the same as what am I trying to say here? Got the pairing. Oh, that's the tensor, right? So that's the tensor map. Maybe I should write this as a tensor. That's the tensor map. Oh, I need to have a name for this map on the tensors. Maybe P for pairing because it comes from the pairing. Okay, so here we go. So suppose I apply the pairing map to TU tensor TV. Well, that is the pairing map composed with the tensor map of TU TV. And so what is that? Well, by this commuting diagram, that should just be the pairing of TU TV. But I'm considering a T that preserves the pairing. So this should be UV. But then, hi, Jens. But then UV is, again, just unfolding that. That is P composed with the tensor map on UV. But that is just P applied to U tensor V. So, what does that actually say? So that says that we can translate, if we have some bilinear map on our vector spaces, then asking that bilinear map preserves the inner product. Asking that we have some linear transformation that preserves that bilinear map is the same as saying that linear transformation, sort of the induced linear transformation on the tensor product, preserves this linear map. So the map doesn't see whether you applied T before you applied this map P or not. That's not quite the same as preserving a collection of tensors necessarily, but it's pretty close. So I wonder if we can push it further to that interpretation by looking at so some people actually define tensors to be the collection of bilinear maps, actually. So I like to think about it this way, in this universal property way, like this way where you construct it as a quotient of this vector space here, but there is a way in which you can say, just define, say, BVV, maybe even just call it BV, to be the set of all bilinear maps. All bilinear maps from V cross V to R. And so now maybe if you write in this sense, you could view T as somehow like literally preserving something there. I'm not sure. Given G, what would we take for this V and P though? Well, so your G would be, I mean, everything here is going to be isomorphic. So we're going to be we're going to end up with the same thing basically. Like your P is just like, by this commuting diagram, P, the result of applying P to U tensor V, it just has to be the same thing as the inner product of U and V. So it's really not that much different. Yeah, so that's what P is. I mean, big V can be anything, right? We're just saying, suppose we have some vector space and some pairing. Yeah, but P would just have to be defined by this. But the point is now P is a linear map. P is a linear map because on the level of tensors, for example, alpha U tensor V is the same as U tensor alpha V. So, I mean, is it worth talking about things in this way? Is there any need to? Is there any advantage? Maybe not, but you know, you had the question of if it's possible, and I think it's a fun thing to explore that possibility. Okay, let me finish telling you about one of the favorite isomorphism that I didn't finish writing above. And then it's story time, I think. So, yeah, I love this isomorphism. I don't know why. There's just some things. There's a lot of simple things in math I like, you know? I work with these very, you know, by some people's standards, I work with very, very complicated abstract things. And I really like those too. But you know, so there's just some basic fundamental stuff that just makes me happy. And this is one of them. So it's an isomorphism between, so this is V dual, so it's the dual vector space of V, and the vector space V, and we take their tensor product. And it's isomorphic with the endomorphisms of V, so just all the linear transformations from V to V. And the isomorphism is given by, oh God, am I gonna get this wrong? What was I? Wait, what is the isomorphism? Here I am about to yap about my favorite isomorphism. I want to say it's just, yeah, here's what it is. Wait. No, I have no idea what I'm talking about. No, I think this is what it is. So we need to send it to a linear map. What linear map are we going to send it to? We'll take the linear map that eats in V, or eats in some U, and send it to, well, I need to send it to a vector, right? Well, I've got a vector here. So, and I've got a thing that over here that eats vectors and spits out scalars. So what I'll do is I'll multiply, I'll plug in U to this thing that eats vectors and spits out scalars. Now I've got a scalar, and I'll just multiply V by that scalar. And I claim that this is an isomorphism. Yeah. And by the way, I mean, if you, this is also some of you might have heard of the Kronecker product. Kronecker product of matrices. And by doing this, I mean you can sort of identify V star with V. You can sort of choose an isomorphism where you basically, you know, if you write everything in V as some row vector, right, then you can write everything in V star. You can just call it, if you write everything in V as a column vector, you can write everything in V star as a row vector. And then, so the Kronecker product is some sort of like tensor product of matrices, and you might look at it and be like, oh, why is it defined like that? What does it have to do with this abstract tensor product? You know, I was talking about, so normally Oh, maybe I should have written v and v star on the other side. It doesn't matter. It makes sense either way. But so of course, if you wanted the dot product of these two vectors, you would multiply them on the side that it makes sense for these matrices to get multiplied on, right? That gives you the dot product. But now the Kronecker product allows you to multiply these matrices sort of on the wrong way, right? But the thing that you end up with is some n by n matrix. And this is actually a manifestation of this isomorphism I told you about above, right? Endomorphisms, what are those? Those are just n by n matrices. And here are our tensors, right? So we can imagine those tensors are, those tensors are just something like this. Kronecker products of a column vector and a row vector here. Okay. Yeah, story time, I guess. So, a brief story, I suppose, but this is the funny way that research works sometimes. So, like, my supervisor, we've got a shared door between our offices. We often keep it open because we like to just chat about random stuff. And so, I'm chilling in the office, and he comes in, and he's like, he's like, and at this point in time, he doesn't have in his mind that what he's about to say has anything to do with like the paper we're currently working on. Oh, first, actually, before I say that, no, I'll tell the story first. So he has no idea. He's not thinking this has anything to do with the paper. He's just saying, oh yeah, there's some examples. There's some stuff I want to check in the case where we're looking at SP4, again, over a p-adic field. Well, even more general than QP, but okay, whatever. Which, in terms of whatever the hell fancy, stuff I'm doing is the same as looking at SO5 over the complex numbers, or rather, not the same, but we're trying to probe the p-adic representation theory by studying the complex geometry of this group. And he's like, oh yeah, these would be some nice examples to work out, but he's like, don't worry about them too much, because, this is like, I've got other priorities, right? I've this, paper I'm working on, and other stuff, my thesis project, and blah, blah, blah. So he's like, yeah, don't worry about it. Well, but me being me, I'm like, well, I can't help myself. I have to go do all of these computations now, because of course I do. And so I go and do these computations, and I crunch out these computations, like, oh, wow, these are some interesting things. And then, my main homeboy, who might be watching this stream right now, my main homeboy in the research group, I start chatting with him, and he's like, and so he helps me realize there's some sort of a theorem that proves, I don't know how to say this without saying too much, but we were looking for some non-trivial examples of some things. So, okay, these words may not mean so much to a bunch of you, but so I talked before that I've got these, like, I'm looking at some variety, and I'm looking at the closures of these things and when they're singular. And I wanted examples of something that's called an irreducible equivariant local system on these orbits, on the closure of this orbit, right? And because in this paper I'm working on, we have some theorems that say, oh, if you have an irreducible equivariant local system on this closure, then blah, 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 we get some theorems out of it. And the thing is, the only examples we had until now were just what's called the trivial local system. So you've always got that one. And we just weren't sure, even though we phrased this theorem in a general way that says, oh, this would work for any irreducible equivariant local system, we didn't actually have any non-trivial examples. Which is fine, because actually the case for the trivial sheaf does a lot of work in this paper. It's an important case for us, but we didn't have any examples. So I crunch out these computations, which my supervisor was just sort of like, saying, it'd be nice to have these examples, not having in mind that this should relate to the paper we're currently working on. I crunch out the examples. I then consult with my homeboy about what these examples should mean, and it turns out that we actually this produced an example of a non-trivial local system on the closure of this orbit. And so now that is going to go into this paper that I've been working on. So it's just funny. It's just, I don't know. That's like a story I wanted to share about how research works sometimes. Like, that's how it goes, so sometimes if you just do random nonsense, it works out in your favor. So because I couldn't help myself doing these computations at my supervisor, be like, it'd be nice, and then I'm just like, I love doing, even though I work with abstract nonsense, I do like doing computations. I'll do nasty computation. In my master's thesis, I needed to work out, I wrote so there's some abstract stuff. I had some code that helped. But then, in order to make the code was computing some very abstract things. In order to make sure that I thought the code was working right, I needed to have some small examples worked out by hand. But small in this case meant some very nasty computations. And luckily at the time, I had so I had gone to help my dad. I guess he volunteered. He volunteers sometimes. He volunteered to paint some place, some shelter or something, or no, it's an education set. I don't remember. But anyways, they had these massive whiteboards that cost hundreds and hundreds of dollars. And they're just yeah, we don't use them anymore. So do you want to take them home with you? And I was like, okay, sick. So then I had 3 of my bedroom walls were just these massive whiteboards. And that summer I just, I was just in my room crunching out these horrendous computations by hand. But you know what? I loved it. And then I went and did more abstract stuff, and I loved that too. Anyways, we're getting far off topic here. So actually, in my old videos, you can see some of those. You can see some of those whiteboards, when I'm chatting in the background. I have some video about the non-associativity of rock, paper, scissors, for example. I don't know if you get the full view of that. I was also trying to make something called I only had 3 episodes of a vlog, but I actually called it VV log. So it was vlog, but then I had 2 V's together, so it looked like a W, so it looked like without loss of generality. And I thought that was a very funny pun. Anyways. Ugly computations. Yeah, so we have this terrific example now that works out in our case, and it means something, and it's cool, and there's more things to do and explore here. I just saw the new question in chat. I'll answer in a second. I've one other thing I want to say about this is, this also leads to bittersweet news, though. So not just because of this example, but because of other things. I met with my co-authors last night to discuss what we need to do to get this paper in shape to put on the archive. And Chazzy, holy crap, nice to see you in here, dude. but yeah, I met with my collaborators last night to talk about what we need to do. The paper looks pretty good, but then, we started talking, and partly because of this example, we find more and more stuff. We're like, oh, well, it'd be like really cool to also include this and that in the paper. Which is like, it's bittersweet because like I want to have a paper. I do have one paper from like undergrad research, but this would be my first like big boy paper. So, I'm like hungry to get this out on the archive. So I'm a little disappointed. It's going to take a bit longer now. But okay, it's like we're going to put more cool stuff in the paper. So it's fine. But yeah, got to do some more work because we started talking about the stuff and threads started unraveling and we're like, oh yeah, but what about this? And like, oh, there's this example, like we should check this case. And then, also the discussion led to, or a refinement of a certain conjecture that I'm putting in the paper. And we found a case where it's like, oh, here's why we need like one of these qualifying words to make it work because it fails if we don't put it in. And so yeah, I don't know. That's maybe more of an insight to research there as well. That's kind of how it works. So, but I guess I have to go read more cool stuff over the next couple days. That's the trade-off. Okay, trying to get into math PhD too. Really appreciate the channel. What is the exact topic of your PhD? Yeah, good question. I should just make a video on this. I should make a small series of videos on this where I explain the very rough idea. But I'll try to hone in on it a little bit. So it's hard to ride the line though of being... I want to give you enough precise information. Like I don't want to be too vague, but I don't want to lecture for 3 years here. Actually, that's a lie. I don't. You guys probably know by now. I love not shutting up. Not shutting up is my favorite thing to do. I love it. So maybe I should do like a 24-hour marathon stream for charity where I just see how long I can yap about math for without sleep or taking a break. I bet it's a long time. I bet I could go for a long time. Okay, but my research broadly falls under the local Langlands. He's a talker. Yeah, Chazzy knows. Me and Chazzy go back to Winnipeg. So when he's in the chat saying I'm a talker, like he knows. So we got local Langlands. So very roughly, my research falls into local Langlands. What is that about? Well, generally, Langlands says that there's sort of like nice representations of some group, like GL. GL over what? Well, there's all sorts of different things. They could be Adels, they could be global fields, they could be local fields, they could be all of these weird things can go in here. And there's all of these different versions of Langlands, function fields, whatever. And so the point is just there's certain representations of certain groups, and they should line up somehow with Galois representation. So some like say field extensions of the rational numbers or something. So representations of groups here, but these representations are all kind of living in a world of harmonic analysis. So you've got like L2 kind of, measure theory stuff, inner product stuff is going on over here. Like, so it's like very analysis plus algebra. And then over here, of course, this is like Galois theory is like very number theory. You've got like elliptic curves feed into here. You can sort of construct Galois representations from elliptic curves, things like this. And so it's about matching those things up. Well, my research, I focus on I focus on local Langlands. So that is about, just for simplicity, let's just think about n by n invertible matrices with entries in the p-adic numbers. And that goes, and over here, there's, how do I say? We don't need the full group of like Galois representations. We take some sort of approximation to this. But let me just even circumvent all of that. And the philosophy of my research group, well, not even just my research group, like I think, well, this was pioneered by a lot of people. Like, okay, there's a lot of work that we take from David Vogan, who initiated this stuff, but these ideas even go back further to like Deligne and Lustig and Zelevinsky, and maybe even further than that. But the idea is that somehow if we look at this at the dual of GLN. So earlier, I don't know if maybe you weren't in the stream earlier, but as I was talking about these different groups that we can define, like special orthogonal group and stuff. And I mentioned that there's these special sort of, some of them come in dual pairs. So SO2N was self-dual, right? So that also means when you're studying, say, like a p-adic field, its special friend over the complex numbers is SO2N over the complex numbers. But if you're looking at SO odd over the p-adic numbers, by this sort of duality here, maybe in a future stream I'll explain exactly how this duality works, but you look at SP2N over the complex numbers, that's its dual, and vice versa. So GLN is another one that's self-dual though. So the idea is we want to study the representation theory, so that's like harmonic analysis type stuff. We want to understand the representation theory of GLN over the p-adic numbers. But there's this philosophy that from like Vogan and friends, plus assuming the Langlands correspondence, but I'm just going to like ignore exactly the Galois part and just geometrize it. That should have something to do with the geometry of GLN. And so what I end up studying a lot of, and what like my research group ends up studying a lot of, is actually doing algebraic geometry inside this group and its Lie algebra. So, I do representation theory as well. Like, I do have to think about and prove things and understand things about the harmonic analysis up here. But actually, on a day-to-day basis, I really end up thinking about algebraic geometry. So there's stuff like, so we look at these certain subvarieties of, let's just say, the Lie algebra of GLN. That's just a fancy way of saying n by n complex matrices. But we're looking at a certain special subset of that, and even more special subsets here. And for example, one thing I study is these special subsets I look at, their closures, whether they have singularities or not. And one of the ideas of the research is that these singularities mean something about the representation theory. So the idea is like, I can learn about representations of my original p-adic group by understanding the singularities of these things. So what does that tell me? I mean, that tells me stuff about, like, one way of building. In previous office hours, I talked about, building these representations of GLN by inducing them from smaller representations. And one of the things that these singularities will tell me about is what kind of representations live inside this one, right? So this induced representation in general will be some big representation. It'll contain a bunch of others. And so sort of looking at how bad a singularity might be will give me information about the kinds of representations that live inside here. Just to name a little bit about it. So, okay, I feel like I've already gone, I already went, high level and into crazy land, but that's roughly what my geometry is about. So I would say I work in local Langlands, but actually, I do like differential geometry and algebraic geometry all day. Yeah, so that's basically that. I think that's all for today. It's been about an hour of yapping. So, nice to see you all. Time for you and me to go prove some theorems. Actually, for me, it's time to first hit the gym. You got to keep your body fit to keep your mind fit. And then I have to go comb through a ton of papers to understand these new examples we've uncovered in this paper that hopefully will be out soon. Unless we make even more discoveries and then this grows to a 100-page paper. Who knows? Sounds very interesting. What would I say is the best introductory book on this particular topic? I mean, the introduction topic. Best book. Yeah, may you find the end of your diagram, Chase. May all your diagrams commute. Maybe that should be my new saying, my new goodbye. May your diagrams commute. What would I say is the best introductory book on this topic? Yeah. I don't know. On this topic specifically. I mean, the thing is, yeah, there's some things in this world that have like great books that introduce things, and then there's other things in the world which it's like it's very hard to learn about on your own. You kind of just need to go, like, that's the point of having initially a supervisor who's like, okay, you read this section of this paper and this section of this paper and this section of this paper, and then you sort of get the hang of it, and then you go and you learn about, and then you're like, okay, and then you understand how to swim through things on your own and eat these little bite-sized pieces of stuff. So I don't know, but maybe what I'll say, there's this awesome recent book by Getz and Hahn. Yeah, take care, Chazzy. Have a good day. We should grab coffee soon, by the way. But yeah, I would look at Getz and Hahn first. I mean, there's tons of, but even that is like, they've got more information. It's like an introduction to automorphic representations in general, and so there's a lot of stuff that go beyond the particular thing that I'm zooming in on. You know what I mean? But you could start there with just the p-adic representation theory. The other thing to look up, okay, if you're interested in the particular thing that I'm working on, with complex representations. I mean, the key word of one of the things I'm focusing on is the p-adic Kasdan-Lustig hypothesis. And so there's an early paper by Zelevinsky that's basically of this name. So I would look up that paper by Zelevinsky on the p-adic Kasdan-Lustig hypothesis. But that also uses some, it starts off with some basic combinatorics, and that basic combinatorics is fed into by, there's another paper by Zelevinsky called Representations of p-adic Groups 2. I think that's the name of the paper. But anyways, those are places to start. I mean, okay, probably I imagine if you're reading, if you're just going in blind to those papers, there's a ton of notation. And you're like, what the hell is going on? Like, probably it seem too complicated. But just sit with them for a little bit, because I promise there's stuff like if you just casually read it, I think you'll be able to understand some things. Well, as long as maybe, I don't know, you're guided by Getz and Hahn for the basic representation theory of p-adic groups. Maybe you'll be able to connect those things. So, anyways, now I'm leaving for real, because there's work to do. There's papers to read. So